Good morning, one and all. I am Dr. C. Labesh Kumar from Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal. Today's my topic is related to cutting parameters and tool life. Earlier sessions we already discussed how the merchant circuit diagram involves in making cutting process possible. In today's lecture, we are going to learn about cutting parameters and tool life. So the course outcome after this session, you will be able to know what are the different parameters which are involved in cutting process, as well as how the tool life is calculated, on what relationship the tool life has been determined. Okay, so the cutting parameters generally are segregated into three different types. First one is cutting speed, feed, and depth of cut. So these are the three important parameters with respect to the process of machining. So cutting speed, feed, depth of cut. The process of removing the material depends upon these three parameters, which are very effectively in the process of making the machining possible. Let us see the definitions for each of the parameters. So first of all, we will see the definition related to cutting speed. So it is the speed, the distance traveled by the work surface in the unit time with reference to the cutting edge of the tool. So generally, it depends upon the different type of machines what we are going to use for the machining process. So the cutting speed is the distance traveled by the work surface in the unit time with reference to the cutting edge of the tool. So here, the cutting edge of the tool is very, very important, because if the tool is rotating in terms of milling, the workpiece is to be fed with respect to the tool. The cutting speed generally will denote with respect to V, which is simply referred as speed. Usually it is expressed in the form of meters per minute. If we consider a process of lathe machining operation, that is general turning operation, this is the workpiece. This is the axis of the workpiece, and this is the workpiece which is fitted into the check of the lathe. Now, tool will be moving parallel to the axis of the workpiece. Now, what I can say that the work surface in the unit time travel distance. Otherwise, the speed at which the workpiece is rotating when the tool is moving in the direction parallel to the axis of the workpiece. So generally the expression is meters, movement in meters per minute. So how much distance it is moving per minute in terms of turning operation, that defines the cutting speed. So cutting speed is the distance traveled by the work surface in the unit time with reference to the cutting edge of the tool. This is the tool and this is the edge of the tool. How fast it is moving along the work surface will determine the cutting speed. The next is feed. So feed generally are in two terms. First term will be in the revolution term. The second term will be in the minutes term. So let me come to the definition so that you will have a brief relation in the feed also. So a feed is the distance advanced by the tool into or along the workpiece. Into means going inside the workpiece or along the workpiece. Either direction. Workpiece stands here, machining along the work surface or into the work surface. Both will come into the feed, into or along the workpiece. Each time the tool point passes certain position, it travels over the surface. So each time when it passes over the work surface, so generally it is defined as it is the advancement of the tool into or along the surface of the workpieces, or the movement of the tool or travel of the tool. We have considered two different cases. The first case is related to turning. Suppose we are turning is an example for a lathe machine. So in case of turning, the feed is the distance that the tool advances in one revolution of the workpiece. So generally, if I draw the workpiece diagram, so this is the workpiece diagram in the lathe. So it has a movement. This is the movement inside the check. So when it advances along the workpiece, so this is what for each revolution RPM, how much the tool is getting advanced, this is termed as feed. So feed is very different from cutting speed. Cutting speed is the how fast the movement of your workpiece is getting into contact with the tip of the or edge of the tool is termed as cutting speed. But when it comes to the feed, it is the advancement of the tool for one revolution of the workpiece. If it is in lathe, or if we take other example as milling, so it is expressed in mm per minute. Mm per minute in a sense movement with respect to the workpiece along the surface. This is the tool in the milling and this is the workpiece. Generally, the tool is fed into the workpiece. That is what happens in the milling. So the feed expressed in meters per revolution is with respect to turning operation. That is with respect to turning operation, mm per revolutions. As well as it is expressed in the meters per minute. So meters per minute, how many meters it has been traveled per minute is given in the shaper or a planer or a milling machine. Generally shaper and planer are considered for delivering this feed with respect to the machining operation. So feed is very different when it comes to different operations. So the units for feeds are very different. That is, one is mm per revolution, the other one is mm per minute. So both can be considered for the feed units and generally defined as it is traveling distance of the tool advancement into or along with respect to the workpiece. So this is what called as the feed. Next, the third parameter what we want to discuss is depth of cut. So depth of the cut, generally when we need to remove the material, the tool should plunge inside the workpiece. That plunging inside the workpiece is termed as depth of cut. So I can say in other relations such as the distance through which the cutting tool is plunged into the work surface. Suppose this is my workpiece. If I want to plunge, so this distance up to this point, my tool is getting in contact with the workpiece. Imagine this as a workpiece. Okay, this as a workpiece. Now I need to remove material of this much depth. So my workpiece should get in contact with tool up to this certain. This is what plunging of the tool into the workpiece up to certain distance. So that up to certain distance will come as depth of cut. So depth of cut, in a sense, I can say that the amount of material thickness removed into the one pass of the tool along the work surface. So thus the distance measured perpendicular distance between the machined surface and so after removing this material, so whatever I get here will be the machined surface. Okay, suppose somewhere else this is unmachined surface. Up to here the material has been removed. So up to this point the material has been removed. Now this is unmachined surface, this is machined surface. So the difference between, that is the perpendicular distance measured between the machined surface and unmachined surface, that is uncut surface, or previously machined surface of the workpiece. So this is the machined surface, this is what called as depth of cut. So the term depth of cut is very effective in machining. So it is the plunging of the tool into the work surface. Generally it is measured uncut surface to the cut surface. What is the depth related to the uncut? Generally, it is expressed in the terms of D, that is small d. So we have it in terms of mm, that is millimeters. So general, the relation will be in terms of millimeters. So depth of cut, speed, feed, and depth of cut. So all these three things are the major parameters which are being used when the machining process is carried out. So speed, so revolution is very important. Which direction? Revolution, as well as the movement of the traveling of the tool tip along the work surface. Now, feed can be delivered into two terms, that is mm per revolution or mm per minute. Mm per revolution or mm per minute. So both we can express. Next, depth of cut generally in mm. So how much distance it has been covered or plunged into, where the differences parts along finished surface, that is cut, that is machined surface, whereas the other term is uncut surface, that is non-machined surface. So these are the definitions for speed, feed, and depth of cut. We also express them in terms of units for speed, feed, as well as depth of cut. So meters per minute stands for cutting speed, mm per revolution or mm per minute stands for feed, depth of cut generally expressed in terms of mm. Now, what are the factors which determine speed, feed, and depth of cut, which are very, very important? The factors which contributes for speed, feed, depth of cut. So factors which are contributing for speed, feed, depth of cut is kind of metal being cut. So what type of metal we are going to? Generally, the metal in terms of properties, you have ductile as well as brittle. So we already discussed the speed, feed, depth of cut related to chips. So chip coming out of the workpiece. So that is one factor where you consider kind of the metal which has been used for machining process. So this speed, feed, depth of cut depends upon the kind of metal being used. If it is a ductile material, if the speed, feed are high and depth of cut are very small, you will have continuous chips. So the factors depends upon things which contributes for the machining process very easily. If it is in the brittle material, the speed is very low, feed is very low, depth of cut is also high, then we have discontinuous chips. So it differs between the material to material, what kind of material being cut. So that is what, this is the first factor which contributes for the machining process. The second factor is life of the tool. So this is very, very important, life of the tool. That is what we are going to discuss in the next slides. So life of the tool is very, very important. So the life of the tool should be very increasing mode, not decreasing mode. So life of the tool also depends. If the speed you are going to increase rapidly, the tool life gets decreased. Similarly, with respect to feed and depth of cut. So we need to have control over the process parameters. So these parameters, speed, feed, depth of cut, has very much impact on the machining process. So second factor is being life of the tool, because the life of the tool. So generally, when we talk about machining, three things we need to consider in our mind. The first thing is workpiece. Second thing is tool. The third thing is the chip coming out of it. So workpiece related, tool related, chip related. The second one is your tool. So tool life should be very useful life. If you don't use tool life usefully, then the cost for machining goes on increase. The economic machining will not get satisfied. Next, the third factor is shape and dimension of the cutting elements. So how complex contours we have on the workpiece, the speed, feed, depth of cut varies depending upon the shape and dimension of the cutting elements. So cutting elements are nothing but the parts where the workpiece on which the machining process takes place. For example, if I want to machine only the surface plane, it is very easy to remove the surface plane on a rectangular block. If I want to do a pocket inside the workpiece, so I need to control all the parameters to get perfect pocket. If I don't control the parameters, I can't able to get the desired pocket. So this is the desired pocket. So pockets generally are made on the milling machine. Pockets generally are made on milling machine. So this pocket is present on this workpiece. Imagine this is a workpiece. So if you want to cut a pocket in the workpiece, so it should be very carefully done. So the cutting elements like shape and dimensions of a workpiece is very much impacting the factors which are related to speed and depth of cut. This is the third factor which has been contributing for speed and depth of cut. The fourth is the size of the chip cross section. The size of the chip cross section. We already discussed related to chip which is flowing on the rack face of the tool. Now, the size of the cross section of the chip, okay, if I draw this cross section, okay, depends upon the alteration of the speed, feed and depth of cut. Generally, if we increase the depth of cut, the width of the chip increases, thereby the cross section also increases. So, the improvement in the depth of the cut may affect the process parameters very effectively, and the work surface as well as the section related to the working process also affects. Next, the type of the finish desired. So, finish comes under fifth factor. So, finish there might be necessary for some parts to get a proper finish up to some microns. Okay, if I want to talk, if 1 micron is the surface finish, that is what I require. So, machining that 1 micron is not very simple. So, it depends upon the factors compounding for the machining process. Generally, when speed increases, you have machining metal removal rate very large. If your depth increases, the metal removal rate is also very large. But the required thing is that the surface finish should be very proper. Means the amount of material being removed from the surface when it comes to the very narrow in terms of small chips that we will achieve in the cylindrical grinding as well as surface grinding. So the type of the chip decides whether the surface is getting into a proper output or not. So whatever the surface you want to have or desired surface, we can't get unless until we control the factors which is affecting the process parameters. The process parameters nothing but feed, speed and depth of cut. So these factors are very much important with respect to the type of the surface which you are able to need or you are able to make on the surface. Next, coming to the point number 6, that is factor number 6, it is rigidity of the machine. Machine rigidity plays very major role when it comes to machining any workpiece. So, if the rigidity of the machine is not perfect, thereby the forces compounding on the machine will be very much high. Thereby, we will have much chattering on the surface. So, chattering refers to the uneven surface on the machined element. So, rigidity comes with respect to individual part assembly, overall assembly, as well as the foundation of the machine. If you don't have a proper foundation of the machine, so in turn, it will lose its rigidity, thereby it will affect the machining process. If it is affecting the machining process, indirectly it will affect the factors like speed, feed and depth of cut. If it is affecting the speed, feed and depth of cut, then whatever we desire, either it may be the shape of the workpiece or the dimensional accuracy on the workpiece or the surface finish pertaining to the operation will not be achieved. So that is what the rigidity of the machine is very, very important when the following factors to be determined so that it will have a proper finishing operation on the required machining part. Next, the last one is the point number 7 stands for type of the coolant used. So coolants are used for reducing friction, or I can say it is also used to control the temperature which is producing in the zone 1, zone 2 as well as zone 3. So in our last discussions, we have already discussed what is primary zone, what is secondary zone, what is tertiary zone. Primary zone stands between the tip of the tool to the workpiece engagement. Wherever the shear plane is getting into part, that is connecting into the part, this is where the primary zone is. So the primary zone along the shear plane. So if you can't control this zone when the machining is taking place, what happens? It will affect the due process parameters. That means in the process of making machining, it will affect the relation of the surface as well as the tool life as well as the chip producing outside. So all these things will affect. It is zone 1. Zone 2 also is very important. It is between the face of the tool and the rack face of the chip. So face of the tool, rack face of the chip. So at this junction, you have zone 2. So zone 2 creates very much friction on the tool surface. To overcome that friction, you need to use coolant. So that if you use heavy speeds, feeds and depth of cut, so coolant usage is very recommended. Similarly, at the third zone, that is finished zone, this is unfinished zone. So after you get the finished zone, you need to have some part, that is some coolants requirement. That means not to have a rusting on the finished surface. You may have a property where the coolant gets into the surface and you will have the temperature decrease around the part of the workpiece. Now, so these are all the factors which determine speed, feed and depth of cut. Metal being cut, tool life, shape and dimension of the cutting element, size of the cross chip which is getting out of the machining, type of the finish desired, rigidity of the machine, type of the coolant used. Now coming to the next part, that is nothing but the continuation part of these factors is first, that is tool life. So tool life is very, very important in the machining. So generally it is defined as the useful life of the tool in terms of time or in terms of units. Generally it might be time with respect to units. How much time a tool is being used before getting it to resharp, or how many products you are produced when it is getting blunt. So the start of the cut to some end point defined by the failure criteria. The failure criteria here is nothing but the shape. Generally, the single point cutting tool, we have all 7 angles. If you want to describe, so all the 7 angles should be intact on the surface of the tool. If those angles are not intact, that means it is under the failure criteria. Any angle which has got blunt or it has decreased in the angle, so that will come under the failure criteria. So generally it is defined with respect to the time, whether it is 1 second or 1 hour or 24 hours or 2 days, 3 days, whatever it may be. So starting of an operation or starting of a cut operation to which the failure criteria is termed in general as a tool life. So the tool life which is no longer performing the desired function is said to be failed. That means required surface finish you are not getting. Thereby the tool has been phased or tool has failure in it, or the dimensions what you want to have, it is not getting the proper dimensions when you are applying proper feed, speed and depth of cut, then we can say that the tool has get blunt or failed. The tool may be resharpened and used. This is the other thing. But before resharpening, how many components we have machined or how much time it has been taken to make the operation successful. That is where the term tool life comes into action. Now, measurable quantities for tool life, generally actual cutting time to failure. So actual cutting time to failure, in a sense, failure in the terms of the angles which are present on the tool. If any angle has been disturbed or the tip of the tool has got blunt, that means the tool is a failure tool. Next, the length of the workpiece to the failure. So the length of the cut, suppose this is the length of the workpiece I need to have machining on. Suppose it has started cutting from this direction. Now the tool has got blunt at this point. Now this length will be considered as the length to which the tool has been failed. Next, the volume of the material removed to the failure. So you can have the volume, how much volume it has been removed to the failure point. Next, number of components produced. So number of components is directly nothing but units produced. Next, cutting speed for a given time to the failure. So parameter cutting speed is very much important. So how much speed you are maintaining over a time to the failure. So these are the all measurable quantities of the tool life. Now, modes of the tool failures, either it may be fracture failure or temperature failure or gradual wear. Fracture failure occurs due to the tool when the forces are very high. Temperature failures occurs when the tool undergoes a softened zone at the tip of the tool. Gradually wear gets when the tool loses its rigidity around the neck. So these three things are the mode of the failures of the tool. Generally, the tool life is very expressed in terms of time or in terms of units, or it is a resharpening period between the one operation to other operation. So generally, number of pieces you have machined, total volume removed, length of the cut, limiting value of the surface finish, increase in the cutting forces, dimensional accuracy, overheating and fuming, presence of shatter. So these are all the characteristics where you can identify your tool is getting failed. Now we are into the tool life equation. This is called Vt to the power of n is equal to C, Taylor's tool life equation. So Taylor is a very important scientist who has related Vt to the power of n is equal to C as a tool life equation, where V stands for cutting speed, T in general is a tool life. This is what we are going to derive. Now, N and C are constant. It depends upon the material what we are going to use for machining. There are some contributors where the machining process will take place. In that, N and C both are constant. It depends upon or it differs from material to material. Suppose if I use mild steel as a work material, so for those material, the N value and the C value differs very heavily. Though this is fairly good formula, but it is very narrowly used in the process of cutting region. So the Taylor has compounded other relation where he has included feed and depth of cut as the other parameters which are affecting the tool lives. This is the modified tool life equation. So it was developed by the researcher of a good study about the equation, which is Vt to the power of n is equal to C. V stands for cutting speed, T stands for tool life, N and C are constant, which are depending upon the material what you are going to cut. But the modified tool life equation is Vt to the power of n, F to the power of n1 and D to the power of n2, which is equal to C. Here, those researchers have included feed as a other parameter and depth of other parameters. So we already discussed that these cutting parameters, speed, feed, depth of cut have very impact in the machining. If you want to have tool life derivation or tool life finding, if I use depth of cut very heavily, I can't say that the tool will withstand up to certain time. So immediately when it gets into contact of the workpiece, it may get blunt. So not only cutting process parameters, the tool life depends upon the work material as well as the tool material. So generally, I can say that it only depends upon the feed, speed, as well as depth of cut. It has other parameters where you need to consider as work material as well as tool material. So in general, the tool life is given as Vt to the power of n is equal to C. This is non-modified type of tool-like equation. The other part where we want to have inclusion of feed and depth of cut as the other two parameters for finding the tool life. So we have included into the part. So generally what is happening, if you don't consider feed and depth of cut, only cutting speed if you are going to consider. So the problem here is that you can't exactly find how many units the tool will machine or how much time it will take for machining unless until you include feed and depth of cut. So the process of machining gets very easily, so that you can find how much time or how many units the tool will be intact without losing or without undergoing the failure criteria. So not only the process parameters, that is feed, speed, depth of cut, we need to consider the tool material as well as work material. So tool material also very important, as well as work material also plays a major role for defining the tool life. So generally the tailor has given the relation with only cutting speed. The modified tool life equation speaks about feed and depth of cut. So feed and depth of cut also plays a major role to define the tool life. So generally in the machining process, the tool life should be very high. It should not be very low. If it is very low, you will not have economy in the cutting process. So cutting process, you will not have economy. If it is not in the economy, that means the cost of machining will increases, thereby the burden on the product selling will also be increases, because the product will also cost very high. So in general, we need to finish these things with respect to speed, feed and depth of cut. Then only we have the finding proper tool life. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.